Okay, hello there. In this video, we'll go through example 12.1.3, which I assure you is an entirely made up scenario where we test to see if higher amounts of interrupted sleep cause lower test scores. So we've got this statistics teacher that's gotten students to volunteer to listen to the school fight song loudly on repeat as they attempt to sleep the night before a test. Like I said, totally made up. And the volunteers have been randomly assigned the amount of time for which the recording will play, anywhere between 1 and 7 hours. Do the higher amounts cause lower scores? We're going to find out. We're going to find out by looking at the slope of a regression line, where we've got the hours of messed up sleep as an explanatory X variable. We've got the test scores as a response. And thankfully, we also have the computer regression output, which is going to make our lives a lot easier as far as calculation is concerned, as long as you know how to read and interpret this thing, which I will show you how to do. All right, part A, the question being asked. I see the word cause in there. What allows us to conclude causation in the setup described above? What about generalizing to a population? These are questions we first saw in chapter 4 when we learned the difference between observational studies and experiments. And of course, we can conclude causation if we design an experiment with randomly assigned treatments. In this case, the teacher randomly assigned the number of hours of music playing overnight to the students. Okay, so that's the green light for us. We can treat this as an experiment. Okay. As far as a larger population, we have the volunteers that we have. We can only generalize to a larger population if we had a random sample from that population. So it really depends. Does this group of volunteers represent the entire class? If so, we can generalize to the whole class, but really we can't go too much beyond that. All right, let's move this up here. Part B. State the equation of the least squares regression line. We see a scatter plot of the original data points. We see the regression line drawn in. We can pull the actual equation from the computer output. We've seen this before. You've got two rows in the output, one of which is labeled as constant. The other is labeled based on your explanatory variable. Therefore, the coefficient in the coefficient column is the very same coefficient that would be attached to x in the regression equation. That's your slope right there, is what that is. The other constant would be a y-intercept, so we'll pull that number as well. Remember, the regression line does not represent actual data. As you can see from the plot, it comes close to a couple points, but certainly not close to all. It's a line that's used for prediction. We have to put a hat on the y. Y hat equals 85.706 is the intercept minus 1.117x. If you're going to use y and x, make sure you also remember to define what is the x and the y. All right, so that's a pretty quick, easy pull for part B. And we're going to move down to the next page where the example continues. And here we have a chance to practice the various interpretations that come along with bivariate data. We're going to interpret the slope of the line. We'll interpret r squared, the y-intercept, the standard deviation of residuals. These are all things that we learned in chapter 3. This is really nice review as we get closer to the AP exam as well. Okay, every number that we need to interpret, we can find within the output, which we see again off to the right. Okay, firstly, the slope we talked about, negative 1.117. If you like, you can think of this as a fraction over 1. Okay, 1 being related to x, where the numerator itself is related to a change in y. So we read this number as the amount by which the y variable changes as x changes by 1 unit. So let's put some context on that. X would be hours of music. So we can say for each additional 1 hour of music that a student is exposed to, their test score drops by about 1.12 points. You know that it drops because negative slope. Okay. So make sure you get good context in there. If there's an increase or a drop, make sure that you communicate. Next up is R squared. We see a couple R squareds, but of course we will ignore the adjusted one. We just use the main R squared value. R squared, well, on one hand, it's literally the correlation squared. Okay, we should know what correlation communicates. But when we square the R value, it represents the amount of variation in the Y variable that is explained by the relationship to the X variable. So there's a lot of different reasons that people have different test scores when I give an exam. Okay. Not everyone gets the same score. There's a spread of scores, but there's a lot of different reasons that contribute to people performing differently. And in this scenario, the R squared of 4.7 is telling us that about 4.7, close to 5% of that variation in scores was related to the number of hours of sleep music, I'll call it, in this, again, made up prompt. Okay, so not all, but some of the discrepancies in scores was based on having to listen to that music at night. Okay, so that's what we write, again, with context. Moving on to part three, y-intercept. Of course, you know a y-intercept is a y value when your x is 0. These don't always make sense in context, but you still might be asked to explain what it would mean in context. And keep in mind, this is a prediction or an expectation. It's not necessarily reality. A student with 0 hours of music at night, we would expect to score about 85.7, close to 86. And then from there, as they listen to the music longer and longer, the scores will drop. Excuse me. All right, standard deviation of residuals. We talked about this in chapter 3 as well. It's labeled as S in the bottom left corner. We see a 10.06. Okay. Um, Again, this standard deviation is for residuals, and residuals themselves tie into prediction error. So we can read this number as being, on average, how much difference there actually is between someone's predicted test score from our model and what they actually got. So that's, in the context, that's a rather large uh, standard deviation of residual, which maybe suggests our model isn't super reliable. But we would say predictions of test score based on our model, our LSRL, tend to be off by about 10 points on average. Some are going to be closer, some might be even further away. But that's a full letter grade off on average, so it's a dubious model, perhaps. All right, scroll it just a little bit more here. For part D, we talk about a value we have not used before in these outputs. Looking at the SE column, SE here is standard error, which is a sample deviation. This is now the second standard deviation we're pulling from the output. But the SE coefficient here is meant to be the SEB or SB that was referred to in the reading or reading guide. This is specifically a measure of variation in the slopes. Okay. Whereas the first residual standard deviation was more variation in the y coordinate. This one is for slopes, which is a little bit more relevant for us in chapter 12. We're going to use that slope to determine if there is a relationship or at least a useful relationship between our x and y variables. Okay. So you want to pull the value in the SC column. Make sure you pull the one that literally sits next to your slope in the row for your x variable. You can see that I highlighted it here. We're not going to use the number above that at all in this course. We're going to use this green one. So SCB 0.9472. How do we interpret it? Well, it's telling us um, how our slopes tend to differ for different samples. Okay, we built our model, we built our LSRL off of a particular sample of students. Maybe someone else out there does this experiment with a different collection of students. Do we expect them to have the exact same LSRL as us? No. We understand there's variation. So in a way, our LSRL in itself is a sample LSRL. If you took a population of every student ever and put them through this experiment, I suppose you could say there is a true population LSRL. But we don't have that. We have a sample LSRL. So how much different is our slope from the real one? That's what this number tries to measure. We're going to say on average, slopes of sample regression lines differ from the true slope of a population regression line by about 0.9472. Okay. All right, moving on to part E. Now, in our sample, we have a negative slope, which suggests that the students' test scores are getting lower as the amount of sleep music is increasing. Okay, but is it negative enough? Do we end up with a negative slope just due to random chance? We didn't expect to get a slope of exactly zero, even if the true population slope was zero. So the question becomes, does this negative slope actually provide convincing evidence that more hours of sleep music are causing lower achievement? Is it plausible the association is due to random chance? Okay. Here we have a dot plot showing sample slopes from 100 trials of a simulation. So someone used a computer to model 100 different instances of this experiment, each one with a different group of 30 students, each one with a different sample slope of a regression line. Okay. And the computer model was set up so that there was a slope of zero in the actual population, which again, we don't know if that's the true slope for us, but if there was an X and a Y variable such that the true slope was zero, here we can see just how much variety there is in sample slopes. Sometimes you get positive, sometimes you get negative, sometimes those slopes are pretty extreme in their magnitude. Okay. But here I tried to find all the dots where we had a slope of either negative 1.1 or lower. Okay. And it's not a huge portion of the graph, but it is, reasonably large that I wouldn't say extremely rare. It looks to me that it is possible the association is due to chance variation. Out of 100 trials here, about 11% of them did have slopes less than or equal to ours. So again, not huge, kind of close to a rejection region depending on your alpha, but not quite there. Okay. So that's our first evidence that maybe we cannot say that the music is causing people's scores to get lower. Still a bit up in the air. We're going to do some further analysis. Now, if we were going to move ahead with inference testing here, there are conditions to check, as you know. And here in chapter 12, it is the most epic condition checking you will ever see. Instead of the typical three, we now have five conditions that you already saw in your reading guide. The order that you present them doesn't necessarily matter. So if you wanted to put them in the particular order that you see here, there's a bit of a memory device to it. LINER spells liner, as in line regression. Helps you remember what we're supposed to do. Okay. And for these various condition checks, we need a few different graphs as well. Okay. We look at the original scatter plot. We look at a residual plot. We look at a separate graph of residuals that could be histogram or possibly box plot. This graph to the right is a normal probability plot. We don't really cover that anymore, so you can ignore that one for now. Okay. Talking through the conditions in order, the whole premise of our investigation is that we have a linear relationship. So we now have this new condition to confirm that we actually have a linear relationship between x and y. This is very much the type of analysis we did back in chapter 3. Okay. So this is not really new. It's review. We're seeing a sentence we've written in the past in a new context. You basically look at your original scatter plot. I don't see it here. We'd have to go back up a page or so to look at this graph right here and make a commentary on direction, form, and strength. And that's what we're doing. The scatter plot suggests a maybe weak, maybe mid, negative linear relationship between, and then we got some context between test score and hours of music. Okay. You could give a bit extra about residual plot. Um, I'm not going to require that, but the residual plot we did use in chapter 3 as well to confirm linearity by looking for a consistently random scatter around the horizontal axis. The reason I'm not going to require it is because we're going to say essentially that same thing about the residual plot for a different condition. So it feels a bit redundant to have it twice. All right, next condition, independence. We sometimes called it 10% or 10n check, but we don't check 10n in an experiment. Instead, we just want to comment on the independence of the individuals or volunteers in the experiment. And I think it's safe to say the students' test scores are independent of each other's. We hope they're not somehow influencing each other. Okay, so we'll leave it at that. Um, Normality condition, we've called this large counts in the past. Um, I like N for normal here to help fill out the liner memory device. Okay, for this one, we are looking for normality amongst residuals. We don't care about normality of the x variable or the y variable. Those aren't relevant or necessary. But we hope to see a bell curve spread amongst the residuals, and that's why we have a graph, either box plot or preferably histogram or stem plot of residuals. And the graph doesn't confirm anything. It's kind of like the graph check from earlier chapters where we're just looking to make sure there's no evidence of extreme non-normality. I don't want any outliers or extreme skew. So as you can see, that's what we say about our histogram. It shows no extreme skew or outliers. All right, equal variance. This is the iffiest of our memory device names because really it's a variance or variation or standard deviation condition, but we do want the spread to be roughly equal regardless of the value of x. And this is where we look again to the residual plot, and it's the constantly random scatter is what gives us what we want. We don't want to see a pattern where the residuals are really small on the left and then they get bigger, 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 bigger. That would not qualify as equal spread. Okay. So this consistently random scatter about the horizontal axis, I probably should have put that right here. So on your copy, put this right there. But I do see what I'm looking for here, so we're good to go. Final condition, luckily, is one of the older ones, random condition. Everything we do in this course, we need some sort of randomness involved. We don't have a random sample of volunteers, but that's not the random that I'm looking for here. I need to know we have data from a randomized experiment. So the fact that the treatments were randomly assigned is what clears this for us. Okay, so those are your 5 conditions. You will certainly practice them when you do a write-up, when we do a write-up in the next video. Excuse me again. All right, part G, the very last part. Let's go ahead now and construct a confidence interval for the real slope. We have a sample slope of -1.117. but that doesn't mean the real population LSRL has the same slope. We're looking for an interval of where the real slope might fall. And most importantly, we're paying attention to whether zero's in there. If zero's in our interval, that means zero is a plausible value of the real slope. And zero would indicate that there is not a useful relationship between x and y. There's not a causation relationship. Okay? Zero slope suggests that y value does not tend to change as x changes. So I'm very curious if that's in there. Now, most of what we need mathematically comes from the output higher on the page. There is a single number that we do have to go over to Desmos and grab in just a moment. But first, the formula itself follows the same template as every interval we've done this semester. We take a sample statistic, in this case, a sample slope, plus or minus a critical value multiplier. We're using t here. We don't know population deviations. The degrees of freedom for t is n minus 2 because there are two variables involved. But anyhow, that critical value gets multiplied by the relevant standard deviation, and you do have to be careful because the output shows a couple different standard deviations. We want the one for slope. It sits right next to the sample slope in the output. So that's the SEB. So I'm pulling two numbers from above. My multiplier does not live in an output. Don't be fooled. Let's look at this thing again. There's a T column. It would be very easy to mistakenly pull one of these numbers thinking, oh, my critical value is a T. Let's pull this T. But no, this T column is relevant for a significance test. It is not useful in a confidence interval. Okay, so when we do significance tests, yeah, we might pull one of these numbers, but for today, for right now, no, no, no. So how do we get the value? Well, we're going to jump over to Desmos. Okay, we've got a 95% interval, which is really easy to construct a 95% interval for t in Desmos. So here we are. Go to our plus icon in the top left, open up the inference options. We're going to choose probability distribution. Immediately set this thing to a t distribution. Degrees of freedom, n minus 2 for us is 28. Don't worry about shift or scale. We don't mess with those. We're going to create the distribution. Here is the graph of t. It is not a normal distribution. It does look bell-shaped, but it's got a different spread. It does not follow empirical rule. Let's open up our probability tab. And these region buttons are really nice, okay? Outer, left, right. But for confidence interval, we generally are looking at two bounds that trap an interval between. So I'm going to stick with inner. Okay, right now it's set to be between -1 and 1. That's not what I want. I want to compute the bounds. So I'm going to click the compute bounds button, which allows me to manually insert the area that I want living between my bounds. It's a 95% interval, so let's put a 0.95, and boom, there it is. I've got the plus and minus version of our critical value, 2.048. The visual is a nice bonus as well. Okay, so this is the number that we're pulling, 2.048 is the multiplier. Okay. Um, yeah, from there you can crunch the numbers. Let's see, does Desmos do this for us? Um, well, it very well might, but I'll show you that in a different video when we do an actual confidence interval procedure. Okay, but for now we can crunch the numbers manually. Okay, and what do you know? Zero lives in there, which is problematic for our causation. Okay, first, the actual conclusion. We are 95% confident the true slope of the LSRL for predicting test score from number of hours listening to the music is between -3.057 and +0.823. We do not have strong evidence that listening to the song longer causes lower scores because 0 is in the interval. Okay? That's a wrap for this example video. There will be another video, so stay tuned. Thank you for watching.